Let's begin with something so ordinary that we almost never question it. You walk into a dark room and flip a switch. Instantly the room fills with light. You flip the switch off and darkness returns just as quickly. It feels symmetrical. Light comes. Light goes. Brightness arrives. Darkness rushes in to replace it. But here's the first surprise: darkness doesn't rush in at all. To understand why, we need to slow down and look carefully at what light actually is. Light is not just brightness. It's not simply something that lets you see. Light is a physical phenomenon, an electromagnetic wave. More precisely, it is a ripple in the electromagnetic field that fills all of space. When you turn on a lamp, tiny packets of energy called photons are emitted. These photons travel outward in all directions at an astonishing speed, about 300,000 kilometers per second in empty space. That speed is not random. According to Albert Einstein, the speed of light is woven into the fabric of reality itself. It's not just the speed of light. It's the maximum speed at which cause can lead to effect. Nothing with mass can be accelerated to that speed. No signal can outrun it. It's a built-in limit of space-time. Now pause and consider what that means. When you switch on a flashlight, the light doesn't instantly fill the universe. It expands outward at that fixed speed. If you're standing 1 meter away, it takes about 3/billionths of a second for the light to reach you. That's incredibly fast, but it's not zero. Light has to travel. So what happens when you turn the flashlight off? Common sense says darkness moves in. But physically, something else is happening. When you switch the light off, the lamp simply stops emitting photons. The photons that were already on their way continue traveling forward at the speed of light. Nothing pushes them back. Nothing replaces them. They just move on. Behind the last group of photons, there are no new ones. That region becomes dark. Darkness, then, is not a substance that flows into a space. It is simply the absence of incoming photons. It's what remains when light is no longer arriving. Imagine a long train passing you at night, with every carriage brightly lit. As each carriage passes, you see light in the windows. When the final carriage goes by, suddenly there are no more illuminated windows. Has darkness traveled past you? Not really. The train of light simply ended. The absence that follows is not a thing in motion. It's just the boundary where something stopped. This is our first conceptual hurdle. Our brains are trained to think in terms of objects, things that move, collide, and push one another. But darkness isn't an object. It has no particles. It carries no energy. It exerts no force. It is a description of a condition. Photons are not present here. And that simple shift from thinking of darkness as a thing to understanding it as an absence changes everything about how we interpret its motion. Now let's push the idea a little further, because this is where intuition begins to wobble. Imagine a very long hallway. At one end sits a powerful lamp, shining steadily so that the entire corridor is illuminated. Photons are streaming outward from the lamp, bouncing off the walls, the floor, the ceiling, and eventually into your eyes. The hallway is bright because light is actively arriving at every point along its length. Now suppose someone standing at the lamp suddenly switches it off. What happens next? If you are standing near the lamp, you will see the light disappear almost immediately. But if you are standing very far down the hallway, something subtle occurs. The lamp goes dark at its source instantly, but you will continue to see light for a brief moment longer. Why? Because the last photons emitted before the switch was flipped are still traveling toward you. They do not vanish midair. They do not know the lamp has been turned off. They continue moving forward at the speed of light, just as the laws of physics require. Only after the very last of those photons passes your position does the hallway around you become dark. So what moved down the hallway? It feels like a wave of darkness swept from one end to the other. But in reality, nothing new traveled down the corridor. What traveled were the final photons of light. Darkness was simply the region behind them, the space where no new photons followed. You can think of it like a parade. Imagine a long procession of brightly colored floats moving down a street at a fixed speed. As long as floats keep coming, The street looks lively and full. Now imagine the final float passes by. After it goes, the street appears empty. Did emptiness travel down the road? No. The parade simply ended. The boundary between parade and no parade moved at the same speed as the floats. Darkness behaves exactly like that boundary. And here's the key point. That boundary cannot move faster than the photons themselves. Because it is defined by them, it is the trailing edge of their motion. Now let's scale this up to something cosmic. Light from the sun takes about 8 minutes to reach Earth. That means when you look at the sun, you are seeing it as it was 8 minutes ago. If, hypothetically, the sun were to vanish this instant, Earth would not know right away. For 8 full minutes, sunlight would continue to arrive. The planet would remain bright. Only after the last photons crossed the distance between sun and Earth would darkness finally fall. Again, darkness would not race ahead of light. It would follow the final photons at exactly the same speed. This tells us something profound. Darkness has no independent motion. It cannot outrun light because it is defined by light's absence. It has no engine, no energy, no mechanism of propagation. It is a label we give to regions where photons are no longer arriving. And yet, subjectively, it feels like darkness comes toward us. When a light goes out across a field at night, we see a sweeping dimming. Our brains interpret this as something advancing, but what we are really witnessing is a change in photon arrival, a shifting boundary between where light is still present and where it is no longer being replenished. The physics is simple. The intuition is not, because we are wired to see motion as something tangible. We expect a thing to be doing the moving. But in this case, the moving thing is not darkness at all. It's the last light leaving. Now we're ready to make things genuinely uncomfortable. So far, darkness has behaved politely. It has followed the rules. It has trailed behind light at exactly the speed light travels. Nothing dramatic. Nothing illegal according to relativity. But there are situations where darkness appears to move faster than light. And this is where language starts playing tricks on us. Imagine you are standing on Earth with a powerful laser pointer aimed at the moon. The moon is about 384,000 kilometers away. When you turn on the laser, the beam takes a little over 1 second to reach the lunar surface. That's because photons, again, travel at the speed of light. Now here's the interesting part. Suppose you sweep your hand sideways very quickly, moving the laser beam across the moon's surface. The bright red dot will move across the moon as you move your wrist. If you move your hand fast enough, that dot can sweep across the lunar surface faster than the speed of light. That sounds like heresy. We just said nothing can move faster than light. But look carefully at what is happening. The dot is not a physical object sliding across the moon. There is no chunk of matter racing from one crater to another. Instead, each point on the moon lights up when photons traveling from your laser reach that particular location. When you tilt your wrist slightly, you are not pushing the existing dot sideways. You are redirecting the beam so that a completely new set of photons heads toward a slightly different spot. Each photon still travels in a straight line from Earth to the moon at light speed. No individual photon moves sideways across the moon's surface. The motion of the dot is simply a sequence of different spots lighting up in succession. This is what physicists call apparent motion. The pattern moves faster than light. Nothing physical does. Now let's make it darker. Place an object in front of the laser so it blocks part of the beam. A shadow appears on the moon. If you move the object quickly, the shadow sweeps across the lunar surface. That shadow can also move faster than light. So now we have a situation where darkness, the absence of laser light, appears to race across the moon faster than the ultimate cosmic speed limit. Have we broken the universe? No, because the shadow is not a thing. It's not made of particles. It carries no energy. It is simply the region where photons fail to arrive. And here is the crucial question. Can you use that fast, moving shadow to send a message faster than light? The answer is no. Even though the shadow's edge can move superluminally, any attempt to encode information into it, it is still constrained by how photons travel from the source. You cannot coordinate changes across distant points on the moon faster than the light that connects them. To see why, imagine two astronauts standing far apart on the moon. You try to signal them by sweeping the shadow from one to the other. The timing of when each astronaut sees darkness depends only on when photons from Earth reach their specific position. There is no physical connection sliding between them across the surface. The shadow's speed is a geometric effect, not a physical transmission. This distinction is subtle but fundamental. Physics does not forbid patterns from moving faster than light. It forbids energy, matter, and information from doing so. A shadow carries none of those. Darkness once again reveals itself as a boundary condition, a shifting edge defined by where light is not. And the universe is perfectly comfortable with boundaries moving in strange ways, as long as the underlying causes obey the deeper structure of space-time. That's the difference between what appears to move and what actually does. At this point, the physics itself isn't the hardest part. The hardest part is our intuition. Human intuition was not built to understand fields, space-time, or the subtle difference between a thing and a pattern. It was built to throw spears, catch fruit, and avoid predators. If something moves, our brain assumes there must be an object doing the moving. If something spreads, we imagine a substance flowing outward. That instinct works beautifully for water, smoke, animals, and rocks. It fails completely for light and darkness. Light feels like a stream of something, and in a sense it is a stream of photons. But even photons are not little glowing beads flying through empty nothingness in the way we imagine tiny baseballs. In modern physics, light is better described as an excitation of the electromagnetic field. And that field is not located somewhere specific. It exists everywhere, even in what we call empty space. When a lamp turns on, it doesn't shoot brightness into a void. It creates oscillations in this ever-present field. Those oscillations propagate outward at a fixed speed determined by the structure of space-time itself. Now here is the subtle shift. Darkness is not the opposite kind of oscillation. There is no negative photon. There is no dark field rippling outward when you turn off a switch. Instead, the oscillation simply stops being generated at the source. The previously emitted waves continue outward, and behind them there is just the field in its undisturbed state. That undisturbed state is what we call dark. But psychologically we experience darkness as something positive. It feels like a presence. A heavy one sometimes. We talk about darkness falling, creeping, spreading. Language reinforces the illusion that darkness behaves like a substance. In reality, darkness is closer to silence. Consider sound for a moment. When a speaker is playing music and you suddenly turn it off, do we imagine a wave of silence traveling across the room? Not usually. We understand that sound is pressure waves in air. When the speaker stops vibrating, the last waves continue outward. After they pass, the air simply returns to its resting state. Silence is not a wave, it is the absence of vibration. Darkness is the visual equivalent of silence. Yet we struggle more with darkness than with silence. Why? Because sight dominates our perception. Nearly half of the human brain is involved in processing visual information. When visual input changes, it feels dramatic. When light disappears, it feels like something arrived to replace it. But nothing arrived. The field simply stopped being disturbed in that region. This difficulty reveals something profound about human cognition. We are object-centered thinkers in a field-based universe. Modern physics, especially after Einstein, teaches us that what is fundamental is not objects but relationships. Relationships between events in space-time. The speed of light is not about how fast something moves like a car on a highway. It is about how events are connected. When the lamp switches off, the lamp stops emitting photons, is connected to the event. You see darkness by a chain of space-time relationships limited by light speed. There is no separate event called darkness travels. There is only the causal structure linking emission and observation. And that structure, invisible, mathematical, unforgiving, is what governs reality. Our struggle comes from trying to compress that deep structure into everyday words like moves and comes and goes. The universe, however, is under no obligation to match our grammar. Now we can go one level deeper, because the real issue here is not light or darkness at all. It is causality. When physicists say nothing can move faster than light, what they really mean is that no cause can produce an effect outside its light cone. That phrase sounds technical, but the idea is simple. Imagine space-time as a kind of fourth-dimensional map. Every event, snapping your fingers, a star exploding, a photon being emitted, occupies a specific location in space and time. From any given event, there is a limited region of space-time that can possibly be influenced by it. That region expands outward at the speed of light. If something lies outside that expanding boundary, it cannot yet be affected. Not because of engineering limits, not because we lack technology, but because the geometry of space-time forbids it. This structure is one of the central insights of special relativity, introduced by Albert Einstein in 1905. He realized that the speed of light is the same for all observers, regardless of their motion. From that single stubborn fact follows time dilation, length contraction, and the absolute limit on information transfer. The speed of light is not merely the speed of photons, it is the speed of causation. Now bring darkness back into the picture. When a light turns off, the event, source stops emitting photons, cannot influence distant locations instantly. The information that emission has ceased must propagate outward at light speed. Observers farther away continue to receive photons until the last ones arrive. So when darkness appears at a distant point, it is not because darkness traveled there. It is because the causal influence of the switch being flipped has finally reached that location. Darkness is the visible consequence of a causal chain completing its journey. This perspective dissolves the mystery. The universe is not policing brightness, it is enforcing causality. Even in cases where a shadow sweeps across a surface faster than light, causality remains intact. The geometric pattern may shift superluminally, but no single event is influencing another faster than light. Each point becomes dark only when the local stream of photons is interrupted, and that interruption is connected to its cause through light speed, limited interactions. You cannot use a fast, moving shadow to create paradoxes. You cannot arrange events so that an effect precedes its cause. The deeper structure holds. And here is something even more unsettling. The speed of light limit is not about electromagnetism alone. It applies to all interactions. Gravitational effects propagate at light speed. Changes in electric or magnetic fields propagate at light speed. According to modern quantum field theory, the fundamental equations of nature are built to preserve this causal order. Why is the universe built this way? We do not know. We can describe it mathematically with extraordinary precision. Experiments confirm it again and again. Particle accelerators, atomic clocks on satellites, observations of distant supernovae all agree with relativity's predictions. But the deeper why remains open. Why should space-time have this structure at all? Why should there be a universal speed limit woven into its fabric? Darkness, in its quiet way, points directly at that mystery. It tempts us to think something strange is outrunning light. But when we look carefully, we find instead that the real story is about how rigidly the universe protects the order of cause and effect. Darkness does not challenge the rule. It reveals how carefully the rule is enforced. And in doing so, it shifts our attention from the drama of moving shadows to the deeper architecture that makes any motion, light or otherwise, possible in the first place. Let's step back now and look at the bigger picture, because something even more unsettling is hiding underneath this discussion. We've been talking as if space is a stage and light moves across it like an actor crossing a floor. That's the everyday image. Space is empty. Objects move through it. Light travels through it. Darkness fills it when light is gone. But modern physics does not describe space that way. In relativity, space and time are not passive backgrounds. They are woven together into a single structure, space-time, and this structure is not rigid. It can bend, it can stretch, it can expand. The speed of light is not just a speed limit inside space-time. It is a property of space-time. This becomes especially clear when we look at the universe on its largest scales. Distant galaxies are moving away from us. In fact, the farther a galaxy is, the faster it recedes. This observation, first measured by Edwin Hubble, led to the conclusion that the universe itself is expanding. Now here's the strange part. Some galaxies are receding from us faster than the speed of light. That sounds like a violation of everything we just said. But it isn't, because those galaxies are not moving through space faster than light. Instead, the space between us and them is expanding. The distance grows not because they are racing away like rockets, but because the fabric of space-time itself is stretching. Relativity forbids objects from moving through local space faster than light. It says nothing about space itself expanding. This distinction is subtle, and it's deeply uncomfortable for intuition. We want to imagine expansion as something happening inside space. But according to the equations of general relativity, space is what's doing the expanding. Now connect this to darkness. When we look out into deep space, we see mostly darkness. Between stars and galaxies, enormous regions contain very few photons reaching us. That darkness is not rushing toward us from some cosmic boundary. It is simply the absence of light emitted in our direction, or light that has not yet had time to arrive. In fact, when we observe extremely distant galaxies, we are looking back in time. Their light has been traveling for billions of years. Beyond a certain distance, there are regions of the universe whose light will never reach us because space between us and them is expanding too quickly. There are places we will never see, not because darkness is hiding them, but because their light cannot cross the expanding space-time separating us. This introduces a humbling idea. The observable universe is not the whole universe. It is only the region from which light has had time to reach us since the beginning of cosmic expansion. Darkness on cosmological scales is not an invading force. It is the limit of our causal contact. And here we arrive at something profound. The speed of light defines not just motion, but knowledge. You cannot know about events beyond your light horizon. Not yet. Perhaps not ever. The structure of space-time limits what information can reach you. Darkness, in this sense, is epistemological. It marks the boundary between what can be known and what remains causally disconnected. So when we ask whether darkness moves faster than light, we are really probing something deeper. We are confronting the architecture of space-time itself, the rule that no influence outruns the geometry that connects events. Darkness is not breaking that rule. It is a reminder of it. And on the largest scales imaginable, it quietly defines the edge of our visible reality. Now let's reflect on what this really teaches us about the universe and our place within it. All the examples we've explored, hallways, laser beams, shadows, distant stars, share a common theme. They show that what we perceive as motion speed, and even the passage of time, is deeply tied to relationships between events, not to things themselves. Darkness appears to move. Shadows can sweep faster than light. Galaxies recede at superluminal speeds. And yet, in each case, the fundamental physical laws remain unbroken. The universe is consistent, but our intuition struggles to catch up. This struggle arises because human cognition evolved in a very narrow domain. We live in a world of solid objects, of forces pushing on surfaces, of cause and effect chains that we can see directly. Our brains are wired to assign agency, substance, and momentum to anything that changes or moves. Darkness, however, is not an agent. It has no mass, no energy, no trajectory. It cannot push or pull. Its motion is always defined by the absence of something else, by the trailing edge of light, by the limits of causality. Even more subtly, the rules that govern the universe are based on fields and relationships. Space-time tells photons how to travel. Photons define the arrival of light. The absence of photons defines darkness. Nothing is being transmitted faster than light. No energy is being created. No information is being cheated into the past. Yet our language and intuition insist on treating darkness as if it were a traveling thing, a substance that must move, a wave to catch. This mismatch between human intuition and the underlying physics is why the concept seems shocking. Consider quantum fields for a moment. The vacuum is never truly empty. It seethes with potential, with virtual particles appearing and disappearing, with fluctuations that obey the uncertainty principle. Darkness, in a sense, is just a macroscopic manifestation of the same principle absence defined by what is not there rather than by what is. It is the quiet stage on which the drama of photons and fields unfolds, not an actor in its own right. Now imagine looking at the night sky. Each star you see is sending photons that began their journey thousands, millions, or billions of years ago. The darkness between the stars is not rushing toward you. It is simply where light has not yet arrived or may never arrive. Those regions are empty in one sense, but filled with the potential for light and matter to exist. Darkness is intimately tied to the structure of space-time itself, marking the boundaries of causal influence, the edges of what can affect you and what you can ever know. This is the ultimate lesson. Reality is not built from objects racing through space. It is constructed from events connected by immutable relationships, governed by the geometry of space-time. Speed limits, boundaries, and even absence are defined not by substance but by rules. Darkness does not move faster than light. It is a boundary defined by the universe's constraints. Its motion is the reflection of deeper truths about causality, connection, and the limitations imposed by the cosmos. In observing darkness, we are confronted with something profound. We are reminded that our sensory impressions, our intuitive understanding of the world, are often inadequate to describe the universe. The edges of perception, the trailing boundaries of light, the limits of observation, these are what shape reality more fundamentally than anything we can touch or measure directly. Darkness teaches us humility, curiosity, and precision. It is not just an absence. It is a lens into the deeper structure of the cosmos, showing us that the universe is far stranger, far more elegant, and far more interconnected than our everyday experience ever suggests. In this sense, darkness is not just nothing. It is a guide to understanding what is. It is a reminder that the universe operates according to patterns, relationships, and limits far more subtle than human intuition can naturally grasp. And seeing it this way transforms the way we look at reality itself. Let's take one final step and consider the philosophical weight of what darkness reveals about the universe. At first glance, darkness seems simple, just the absence of light. But once we peel back the layers, we see that it is a gateway to understanding the architecture of reality itself. What feels immediate, solid, and obvious is often a surface impression masking a deeper, more subtle structure. When we flip a switch and a room goes dark, we think we see a movement, a creeping invasion of shadow. But physically nothing moves independently. Darkness is simply the region left behind as photons cease to arrive. That absence is shaped by the speed of light, by the trajectories of photons, and by the causal links connecting the source of light to the observer. It is a boundary, a marker, a signal of where the universe's rules limit what can be experienced or known. This idea scales from a small hallway to the vastness of space. Between stars, galaxies, and clusters of matter, darkness defines the limits of visibility, the edges of causal contact, and the regions where information has not yet arrived. On cosmological scales, darkness is both literal and conceptual. It marks the horizon beyond which the observable universe ends, and with it the limits of what we can ever measure, know, or interact with. What makes darkness intellectually shocking is that it exposes the limitations of human intuition. We're used to thinking in terms of objects, in terms of forces and motion. But the universe does not conform to this simple framework. Fields, events, and space-time relationships govern everything. Light travels, photons move, and interactions occur. Darkness is the absence of these interactions. It is not a thing. Yet, because our minds are object-oriented, we instinctively perceive it as a moving presence. Our experience is shaped not by the fundamental rules, but by our evolutionary need to interpret surfaces, patterns, and motion in a survival context. Physics forces us to rethink this, replacing intuitive images with precise, abstract relationships. In this way, Darkness becomes a lens for understanding causality and the speed of light. The speed of light is not merely a limitation for photons or a measure of how quickly we can send signals. It is a fundamental rule that organizes space-time itself. It defines what can influence what can be known and what remains forever beyond reach. Darkness illustrates this rule perfectly. It is not a messenger racing ahead of photons. It is a consequence, a reflection of the ultimate speed limit and the causal structure that governs the universe. Shadows can sweep faster than light. Dots can move across surfaces seemingly instantaneously. Galaxies can recede faster than light due to cosmic expansion. Yet in all cases, the deeper order remains unbroken. Nothing physical or informational outruns the geometry of space-time. Darkness shows this subtly, elegantly, and persistently. The final lesson is profound. Reality is not a collection of objects moving through empty space. It is a web of events connected by precise, unbreakable relationships. The boundaries of light and the absence of it, the apparent motion of shadows, the expanding universe, all of these reveal that the universe is a structure of interactions, not substances. Darkness is not nothing. It is the visible sign of the limits of influence, the shape of causality, and the edge of what can be known. Recognizing this transforms how we see everything. The next time you switch off a light, the darkness that fills the room is not just emptiness. It is a silent teacher, showing us the elegance, subtlety, and profound order that underlies reality itself. Understanding darkness this way changes how we perceive motion, time, and existence. It forces us to see that the universe is far more relational, ordered, and interconnected than our everyday experiences ever suggest. Darkness, in essence, is the universe speaking to us in the language of absence, reminding us that what is not there can be just as revealing as what is. It is a boundary, a signal, and a guide, and through it, we begin to glimpse the extraordinary architecture of reality itself. To fully appreciate the implications of darkness, we have to consider the interplay between perception, physics, and the underlying architecture of the universe. Darkness is more than simply the absence of photons. It is a manifestation of the way the cosmos organizes information, energy, and causality. Every moment that darkness seems to arrive somewhere, it is actually tracing the edges of what is possible within space-time. It is not a substance racing ahead, but a reflection of boundaries defined by the universe itself. The speed at which darkness appears to move is entirely dependent on the motion of light and the causal chains that connect events. When a light goes out, the absence of photons propagates in the sense that observers notice the change only after the last photons arrive. Each photon moves at the speed of light, and the dark region is simply the gap left behind. The motion of darkness is entirely derivative, entirely relational. This means that darkness is not governed by forces or energy. It is governed by constraints. The constraints are the structure of space-time, the arrangement of fields, and the speed limit encoded in the universe. We perceive darkness as dynamic, but its dynamics are emergent, not fundamental. Consider a cosmic perspective. The light from distant galaxies travels for billions of years before reaching us. In many regions of the universe, light has not had the time to arrive, or it may never reach us due to the expansion of space. Darkness fills those regions from our perspective, but it is not a moving entity. It is a representation of causal separation. It is where the universe's structure restricts the propagation of energy and information. Darkness, therefore, becomes a visual expression of the ultimate limits of knowledge. It is both a physical and epistemological boundary, a signpost of the finite speed at which causes can produce effects. Human cognition struggles with this because our brains evolved in a world dominated by direct physical interactions. We deal with objects' forces and predictable motion. We are not naturally equipped to grasp abstract relationships in fields, causality, or the limitations imposed by space-time. When we perceive darkness moving, our intuition interprets it as a traveling substance because we cannot easily conceive of a boundary or absence defining a movement without a thing that moves. Yet physics forces us to discard this intuition revealing a more subtle relational universe. Even on a smaller scale, apparent faster than light phenomena like sweeping laser dots or moving shadows reinforce this distinction. The pattern can move across a surface faster than light, yet no single particle or piece of information violates the speed limit. The universe allows the appearance of superluminal motion in patterns precisely because they carry no energy or information independently. Darkness behaves similarly. It can appear to advance, but it does not carry any causally effective influence. It is a passive reflection of limits, not an active agent. This perspective changes the way we understand both reality and observation. The universe is not a collection of moving objects with empty space in between. It is a network of relationships, interactions, and constraints. Light defines the reach of causality. Darkness reveals the boundaries that arise when those causal chains end. Observing darkness becomes an exercise in seeing the universe's rules at work, rather than seeing a substance or force in motion. It demonstrates that absence, limitation, and boundary are as physically and conceptually real as energy, matter, or motion. Darkness in this sense is not nothing. It is a subtle guide showing the structure of reality, the organization of space-time, and the limits of influence and knowledge. Through understanding darkness, we glimpse the universe not as a collection of objects, but as a coherent, ordered, relational system, elegantly constrained and profoundly interconnected. To take this even further, we need to examine what darkness teaches us about observation, measurement, and the limits of human knowledge. The universe is a network of events connected by causal chains that operate within strict boundaries defined by the speed of light. Darkness is a visual manifestation of these boundaries. It is where photons have not yet arrived or may never arrive, marking the limits of what can be observed. In that sense, darkness is intimately tied to knowledge. It is not merely the absence of light. It is the absence of accessible information about regions of space and time. Imagine standing on Earth and observing a distant galaxy billions of light years away. The light reaching your eyes today started its journey long before humans existed. In the vast space between you and that galaxy, there are regions where light is delayed, stretched, or even permanently blocked by cosmic expansion. Those areas appear dark, yet they are not empty in an absolute sense. They contain matter, radiation, and events unfolding independently of your perception. Darkness is not moving toward you. It is a marker of causality, a boundary signaling where information has not yet reached your location. Human intuition struggles with this concept because we are wired to perceive causality and motion in terms of objects and forces that interact locally. When a shadow sweeps across a surface or a room goes dark, our brain interprets it as something moving or arriving. But physics teaches us that what we perceive as motion in these cases is often an emergent property of patterns or boundaries. The actual carriers of energy, the photons, obey the speed limit of light. The apparent motion of absence, of darkness, is a reflection of the geometry of space-time, not an independent phenomenon. This also has profound implications for how we understand the universe on the largest scales. The cosmic horizon, the farthest distance from which light can reach us, is a boundary beyond which we cannot acquire information. That boundary defines the edge of our observable universe. Beyond it, the universe continues, but we cannot see it. Darkness is both literal and conceptual here. It marks the regions outside our causal reach. It is the limit imposed not by lack of interest or inadequate instruments, but by the structure of space-time itself. The universe enforces these boundaries, and darkness is the visible expression of those constraints. Even in quantum physics, darkness can be interpreted as a consequence of deeper rules. The vacuum is never truly empty. It fluctuates, giving rise to temporary particles and fields. What we call dark regions are places where certain excitations, such as photons in a specific wavelength, are absent. These absences are constrained by interactions and boundary conditions in the fields. They do not propagate independently, yet they define observable structure. Just as a shadow is defined by the obstruction of light, the apparent movement of dark regions in space is determined by where photons have traveled and where they have not. Ultimately, darkness teaches a profound lesson about reality. It is not a substance, but a signpost. It signals the boundaries of what can influence what, the limits of observation, and the structure of space-time. It reminds us that the universe is relational. What exists, what moves, and what can be known is defined by connections and interactions, not by isolated objects. Darkness is not a failure of light. It is a revelation of order, a guide to understanding the architecture of reality, and a subtle but unmistakable illustration of the universe's deep and elegant structure. To complete this journey, we can look at darkness as a profound illustration of the subtlety and elegance of the universe, revealing truths that are rarely obvious but always present. Darkness is not merely the absence of photons. It is a boundary defined by the interplay of light, space-time, and causality. It exists wherever light has not arrived or has ceased to propagate, marking the limits of influence and knowledge. In this sense, darkness is inseparable from the structure of reality itself, and understanding it requires a shift in perspective from objects to events, from substances to relationships. Consider the everyday experience of turning off a light. The room goes dark instantly, or so it seems. In truth, the photons emitted by the lamp before it was switched off continue to travel through the air, bouncing off surfaces and reaching observers a tiny fraction of a second later. Darkness does not rush in to replace them. It only becomes apparent where photons cease to arrive. Our perception interprets this absence as motion because our brains are attuned to track changes, patterns, and edges. Physically, nothing has moved independently. Darkness is not a substance racing forward. It is the consequence of light's termination, a boundary emerging from the interplay of emission, propagation, and observation. On cosmic scales, the concept becomes even more striking. The universe is vast, and the light from distant galaxies can take billions of years to reach us. Regions of space where light has not yet arrived appear dark, but they are not empty in any absolute sense. Matter exists, stars may shine, events unfold, but the causal chain connecting those events to us has not yet completed. Darkness is, in effect, a record of causality's limits. It is a visual representation of the universe's speed limit, highlighting the ultimate role of the speed of light as the arbiter of influence. What appears as empty space or advancing darkness is really a boundary that defines the observable universe. It delineates what can affect us, what we can measure, and what remains forever beyond reach. Apparent superluminal phenomena, such as sweeping shadows or moving laser dots, further challenge intuition but reinforce the same principle. The pattern can move faster than light, yet no particle, no photon, and no information exceeds the cosmic speed limit. The apparent motion of absence is a geometric effect, a reflection of causal structure, not a violation of fundamental laws. Darkness, in these cases, is a passive manifestation of boundaries, not an active agent. It obeys the rules of space-time while challenging our assumptions about motion and substance. Quantum mechanics adds another layer of complexity. The vacuum is never truly empty. Virtual particles, fields, and fluctuations constantly populate space. Dark regions in this context are defined by the absence of certain excitations or interactions. They are not voids, they are potentialities constrained by boundary conditions, by the laws governing energy and information transfer. Darkness is an emergent property of fields, interactions, and the limits imposed by relativity. Ultimately, darkness is a window into the relational nature of reality. The universe is not a collection of objects moving through empty space. It is a web of events and relationships structured by the speed of causation, by space-time geometry, and by the rules that define influence and observation. Darkness is the silent teacher in this web, showing us where light ends, where causality limits action, and where knowledge is constrained. By understanding darkness in this way, we see that absence is not emptiness but a signal, a boundary, and a guide. It reveals the universe as a network of interconnections, constrained, elegant, and deeply relational, transforming the way we perceive motion, light, and the very fabric of reality.